On October 29th, 2025, the interstellar visitor 3I/Atlas flared so brilliantly near the Sun that it defied every expert prediction, coinciding precisely with a relentless bombardment of massive solar eruptions raging across the far side of our star. Scientists scrambled to verify the comet's trajectory. Not a trace of deviation was found. If the allure about 3I/Atlas's super brightening sounds terrifying and sensational, the real danger may be hovering above our heads, not speeding in from stars, but brewing on our own sun. What exactly transpired when space weather and an alien wander collided? The answers could reshape what you expect in the days ahead. At 1.1.36 astronomical units from the Sun, 3I/Atlas reached its closest approach on October 29, 2025. The energy environment at that distance is anything but subtle. Solar irradiance reaches approximately 735 watts per square meter, a level that dwarfs the deep space background by more than 15 orders of magnitude. For comparison, the same object drifting between stars would experience less than a 10 millionth of a watt per square meter, barely enough energy to warm a single grain of dust. This sudden exposure to intense sunlight is what drives most comet activity. As a comet approaches the Sun, surface ices heat up and begin to sublimate, releasing gas and dust into the void of space. For 3I/Atlas, the thermal load at perihelion should have triggered a predictable rise in brightness, following models built from decades of observing Oort cloud comets. The physics is straightforward. At 1.36 astronomical units, solar energy is about 54% of what Earth receives, more than sufficient to power outgassing and dust jets. Yet the observed brightening far exceeded what this energy input alone could explain. The baseline physics, solar flux, heliocentric distance, and standard sublimation rates set the stage but left a gaping chasm between expectation and reality. As the comet moved through this raw solar environment, it became clear that something beyond simple sunlight was at work. The need to search for external triggers, not just intrinsic comet activity, became unavoidable. Between October 19th and 29th, the Sun's far side unleashed a relentless sequence of powerful coronal mass ejections, CMEs. Helioseismic mapping revealed that several active regions, already sprawling and unstable, were expanding and merging out of sight from Earth. Over those 10 days, multiple CMEs erupted in rapid succession, each carrying billions of tons of plasma and tangled magnetic fields into the inner solar system. These eruptions weren't minor events. Several reached speeds exceeding 1,200 kilometers per second, fast enough to sweep up ambient solar wind and carve massive shock fronts through the heliosphere. Solar monitoring teams tracked these far-side blasts using stereo-wave spacecraft and helioseismic data, piecing together the evolving solar landscape like detectives assembling clues. Some of the largest ejections were modeled to cross the orbital path of 3I/Atlas just as it neared perihelion. While the comet was hidden from ground-based telescopes, the timing of these solar events raised a compelling possibility that Atlas was directly exposed to multiple CME impacts within hours of its closest approach. The significance of this barrage goes beyond sheer frequency. As active regions grew and merged, the Sun's magnetic complexity increased dramatically, creating a turbulent environment for any object passing nearby. Each CME delivered a surge of energetic particles and electromagnetic fields, conditions known to trigger dramatic changes in cometary comas and tails. The overlap between the solar storm window and the comet's sudden brightening pointed to a critical external influence, one that could not be explained by sunlight alone. This 10-day eruption cluster set the stage for the extraordinary photometric evidence that followed. Photometric analysis of 3I/Atlas near perihelion revealed a brightness curve that stands out even among the most active comets ever observed. Using stacked coronagraph data from SOHO C2 and C3 instruments, along with stereo ASOR1, astronomers measured the comet's apparent magnitude as it approached and rounded the Sun. The results were striking. The rate of brightening followed a power law close to our caret-7.5, with an uncertainty of about plus or minus 1. This value is more than double the typical r to the power of -3, or r to the power of -4 seen in Oort cloud comets, and far steeper than any pre-perihelion model had projected for an interstellar object. The photometric pipeline combined multiple color filter stacks, blue, orange, and clear, each sensitive to different molecular emissions. The blue stack in particular captured strong C2 swan band emissions, while orange was dominated by NH2. Both showed the comet shining up to 0.7 magnitudes brighter than in clear light, indicating a surge in gas-driven activity. These measurements were cross-checked between instruments, with COR1 readings offset by 0.4 magnitudes to align with the C3 clear baseline. Systematic uncertainties from background subtraction and aperture choice were carefully considered. But even the most conservative error margins could not account for the steepness of the observed slope. This Arcara-7.5 curve means 3I/Atlas's total output increased by more than a factor of 300 as it halved its distance to the Sun. The anomaly was not a subtle uptick, but a dramatic and sustained rise captured across independent data sets. Such a rapid escalation in brightness demands a mechanism beyond normal solar heating, setting the stage for deeper questions about what triggered this outburst. Every major comet outburst raises a question. Did something alter its path? For 3I/Atlas, the answer comes from careful scrutiny of the numbers. On October 29th, as the comet rounded the Sun at 1.36 astronomical units, the NASA JPL Ephemeris team released their latest orbital solution. Using position data from SOHO, Stereo A, and other space-based assets, they compared the comet's actual track against a predicted hyperbolic path. No measurable deviation appeared. The calculated position matched the model within the expected margin of error, even after the surge in brightness and the barrage of solar activity. This means that despite the dramatic outgassing and possible mass loss, 3I/Atlas did not alter its course. Its velocity and trajectory still fit the profile of an interstellar visitor, not a solar system object. The hyperbolic excess velocity, what marks it as gravitationally unbound, remained unchanged. JPL's orbital solution, time-stamped October 29th, confirmed that the comet would continue outward on track for a Jupiter-side exit from the solar system. For planetary defense teams and the public, this is a key point. There is no evidence the object is on a collision path with Earth or any planet. The integrity of the trajectory, checked by independent analysts and cross-validated with multiple instruments, rules out any sudden threat from the comet itself. The story for now is not about a rogue object veering off course, but about the indirect risks that come from the Sun's activity and the space weather environment it creates. The focus shifts from orbital mechanics to what solar eruptions might do as active regions rotate toward Earth in the days ahead. Detecting a faint interstellar visitor against the overwhelming glare of the Sun demands more than just advanced hardware. It requires a network of determined observers and the right tools to tease a signal from noise. As 3I/Atlas slipped behind the Sun, ground-based telescopes lost sight, but spaceborne coronagraphs, SOHO C2 and C3, and Stereo ASOR1, kept recording. The comet's image, buried in streams of solar wind and coronal haze, was not visible in a single frame. Instead, astronomers, many working from home labs and amateur collectives, turned to a method called shift and add stacking. This technique involves aligning and layering dozens, sometimes hundreds, of images along the predicted path of the moving comet. Each frame on its own may show nothing but background glare, but stacking them with the right offset for the comet's motion lets a faint signature build up while random noise fades away. In late October, 2 amateur astronomers working independently detected the first sign of the outburst using this approach. They compared their results in real time over a Discord channel, sharing raw data and processing scripts. Their stacks revealed a clear, repeated brightening in both the C3 blue and orange filter sets, evidence that with careful technique, even non-professionals could contribute to the discovery. The results didn't stand alone. Professional teams ran their own reductions using similar stacking routines and cross-referencing the amateur findings. Multiple data sets, each processed separately, converge on the same photometric curve. This redundancy and the transparency of the workflow built confidence in the measurements. Space-based assets provided the raw images, but it was a collective effort, citizen scientists and professionals together, that made the detection robust. The numbers held up under scrutiny, setting a solid foundation for analyzing the comet's physical changes in the days that followed. The physical structure of 3I/Atlas, as revealed by coronagraph and heliospheric imager data, stands out as much as its brightness curve. Instead of the classic symmetric coma and sweeping tail seen in most comets, Atlas displayed an irregular, asymmetric envelope of gas and dust. The coma spread unevenly, with denser regions offset from a nucleus and a diffuse, almost lopsided glow. The tail, usually a comet's most dramatic feature, was notably subdued, sometimes little more than a faint streamer, barely distinguishable from the background solar haze. Stacked images from SOHO C2 and C3 instruments, along with stereo SOAR-1, consistently showed that the coma extended farther on one side, suggesting a directional release of material or perhaps even fragmentation. The nucleus itself remained unresolved, hidden within this haze, but the overall shape hinted at a physical process not dominated by steady sun-driven sublimation. Instead, the structure suggested abrupt or uneven outgassing, possibly triggered by external factors. Some color stacks revealed localized brightness enhancements in the blue and orange bands, likely tied to molecular emissions from volatile jets. Yet the expected dust tail, bright, straight, and aligned to the solar wind, never fully developed. Instead, the tail appeared weak, sometimes curving or breaking up, and at times seemed disconnected from the main coma. These anomalies narrowed the field of plausible explanations. The evidence pointed toward a nucleus responding to more than just sunlight, and a coma shaped by forces beyond the usual thermal drivers. The puzzle deepened. What could account for such an odd, asymmetric structure in the wake of a historic brightening event? Solar physicists and comet researchers now turn to the plasma environment to explain the extraordinary brightening of 3I/Atlas. As the comet rounded perihelion, it wasn't just sunlight at work. The 10-day barrage of far-side coronal mass ejections had flooded the inner solar system with shocks, high-speed plasma, and intense bursts of extreme ultraviolet and X-ray radiation. Each CME carried its own wave of energetic particles, compressing and stirring the solar wind into a turbulent high-pressure sea. When a comet like 3I/Atlas passes through these conditions, the nucleus and coma are exposed to far more than thermal heating. Charged particles from CME shock slam into the surface at thousands of kilometers per second, driving a process known as sputtering. This bombardment can rip molecules and dust grains free from the surface, even in regions where sunlight alone would not be enough to trigger outgassing. At the same time, the surge in extreme ultraviolet and X-rays boosts ionization rates inside the coma, breaking up molecules and creating a cascade of radicals, CN, C2, OH, seen as strong emission lines in the stack photometry. The sudden compression from a passing CME can also squeeze the coma, raising local plasma density and temperature. These conditions accelerate dust fragmentation, releasing fine particles that scatter more sunlight and spike the comet's apparent brightness. Unlike the smooth, predictable ramp of thermal sublimation, plasma-driven outbursts are abrupt, chaotic, and can drive brightness increases by factors of 10 or more within hours. The timing fits perfectly. The strongest CME arrivals, modeled by Stereo A and SOHO teams, overlap with the steepest rise in Atlas's light curve. The odd asymmetric coma and weak tail structure further support a scenario where external plasma forces, not just the sun's heat, dominated the comet's behavior. For comet scientists, these plasma interactions offer a powerful, testable explanation for the superbrightening and set the stage for targeted observations as Atlas continues outbound. The next opportunity to track 3I/Atlas falls to the ESA JUICE spacecraft. On November 2nd and 3rd, JUICE's unique orbit around Jupiter offers a clear, unobstructed view of the comet as it emerges from behind the sun. The mission team has reserved a 48-hour observation window, redirecting science payloads and shifting deep space network time to capture images and spectra. This is no routine task. JUICE was never designed for rapid comet follow-up, and a last-minute pivot required coordination across multiple mission teams. The goal is to secure high-cadence imaging and, if possible, catch any lingering outbursts or new structural changes in the coma and tail. Ground-based telescopes will soon join the effort, but only after Atlas climbs far enough from the sun's glare. Mid-November marks the likely return of faint detections from large observatories, with amateur astronomers poised to contribute through long-exposure imaging and stacking routines. For most observers, this means waiting until the comet's elongation grows past 20 degrees and twilight fades. Stacking remains a critical tool. Individual frames will barely register the comet above background noise, but by aligning dozens or hundreds of images along the predicted track, observers can build up a signal and track subtle changes in brightness or morphology. Anyone with access to a moderate-sized telescope and a sensitive camera can participate. The key is patience and careful planning. Check updated ephemerides, use precise tracking, and expect to spend hours collecting data for a single composite image. As the sun's active regions rotate toward Earth, these coordinated observations become essential, not just for understanding Atlas, but for monitoring the evolving space weather environment in near real time. Grid control rooms across North America and Europe are on high alert as solar forecasters track the rotation of several massive active regions onto the Earth-facing side of the sun. The next 2 to 7 days are critical. These regions, responsible for the recent barrage of far-side coronal mass ejections, are now poised to send any new eruptions directly toward our planet. Magnetometer readings already show a persistent G1 geomagnetic storm, with intervals nudging into G2 territory as a high-speed solar wind stream sweeps past Earth. Operators at Hydro-Quebec and PJM have run through their load-shedding protocols, recalling the cascading blackouts triggered by the Halloween storms of 2003. Back then, a series of X-class flares and rapid-fire coronal mass ejections unleashed geomagnetic storms that knocked out satellites, disrupted high-frequency radio, and caused transformer damage across the grid. Today's conditions share more than a passing resemblance. The sun's magnetic complexity is at its highest in years, and the solar wind carries both speed and density spikes. Real-time alerts flow from NOAA's Space Weather Prediction Center to power companies, airlines, and satellite operators. Engineers monitor transformer temperatures and ground-induced currents, ready to isolate vulnerable circuits if geomagnetic indices spike. Satellite controllers, especially for low Earth orbit constellations, watch for sudden increases in atmospheric drag that could throw off orbital calculations or even force emergency maneuvers. Amid all this, the aurora forecast lights up for mid-latitudes, just as it did in 2003. For most people, it's a spectacular light show. For those responsible for keeping the lights on and the data flowing, it's a time for vigilance. The next major solar eruption could arrive with little warning, and the margin for error is slim. The operational focus remains clear. Safeguard critical infrastructure, maintain communications, and keep a close eye on the sun's every move. NASA/JPL ephemeris updates show no deviation from 3I/Atlas's outbound hyperbolic path. Stacked spaceborne imagery and ground-based confirmations verify the anomaly, while morphology remains unusual, a diffuse, asymmetric coma and weak tail, unlike typical solar system comets. The leading hypothesis links this outburst to intense solar wind and CME-driven effects, but the exact mechanisms remain under investigation. As Earth now faces a 2 to 7 day window for active solar regions to rotate into view, operational agencies are on alert for possible G-scale geomagnetic storms, echoing conditions seen during the 2003 Halloween events. The full story of 3I/Atlas is still being written, but the evidence underscores one reality. Our solar system is dynamic, unpredictable, and sometimes dangerous. Vigilance remains essential, not just for understanding mysterious visitors from beyond our solar system, but for protecting ourselves from the tempestuous star we orbit every day. The forecast window closed faster than anyone expected. At 3:47 Universal Time Coordinated on November 4th, SOHO's coronagraphs captured the birth of an X9.2 class flare from active region 13889, now rotated into full Earth view. Within minutes, a coronal mass ejection tore free from the sun's surface, its leading edge clocked at 2,400 kilometers per second. NOAA's Space Weather Prediction Center issued an immediate alert. Impact expected in 17 hours. But this wasn't a single event. Over the next 6 hours, 3 more X-class flares erupted from adjacent active regions, each launching its own mass of magnetized plasma toward Earth. The CMEs were merging, creating what solar physicists call a compound eruption, a rare and devastating phenomenon where multiple shock fronts combine into a single, supercharged wall of plasma. Grid operators had less than a day to prepare for the largest geomagnetic storm since 1859. While Earth braced for impact, ESA's JUICE spacecraft completed its scheduled observation of 3I/Atlas. The results came through the Deep Space Network at 11:23 Universal Time Coordinated, and within an hour, they were racing through scientific circles worldwide. The comet had fragmented. High-resolution imaging revealed not one nucleus, but at least 7 distinct fragments, each trailing its own coma. The largest piece showed continued outgassing, while smaller fragments appeared to be disintegrating in real time, leaving gossamer trails of debris. Spectroscopic analysis detected unusual emission lines, high concentrations of carbon monoxide and molecular nitrogen, volatiles that shouldn't sublimate at $1.36 under normal solar heating alone. The plasma bombardment theory was confirmed, but with a twist. The CME impacts hadn't just triggered outgassing. They had shattered the nucleus. Whatever held 3I/Atlas together through its interstellar journey couldn't withstand the concentrated fury of our sun's magnetic outbursts. The comet was dying, torn apart not by tidal forces or collision, but by the invisible hammer of solar wind and electromagnetic chaos. For the research teams, it was a scientific goldmine. For the public watching the news, it raised an uncomfortable question. If space weather could destroy a comet, what could it do to our technology? The compound CME struck Earth's magnetosphere at 2034 Universal Time Coordinated, 4 hours earlier than the most aggressive models predicted. The initial compression was brutal. Magnetic field readings at ground stations spiked to levels not seen since the Carrington event. Within seconds, the entire sunward side of Earth's magnetic shield collapsed inward, compressed to barely twice the altitude of the International Space Station. Aurora curtains exploded across the sky, visible from Madrid to Dallas, from Tokyo to Mumbai. But the light show masked the real danger unfolding below. Power grids in Quebec tripped first. Geomagnetically induced currents, massive electrical surges flowing to the Earth itself, overwhelmed transformer protection systems. 3 major substations went offline within minutes, cascading into a blackout that darkened Montreal and reached toward Toronto. Operators in the PJM interconnection, serving 65 million people across the eastern United States, watched in real time as ground current spiked beyond red line thresholds. Emergency protocols activated. Load shedding began immediately. Controlled blackouts to prevent catastrophic transformer damage. Entire neighborhoods went dark in a coordinated dance to save the infrastructure itself. It was working, but barely. The geomagnetic storm had rocketed from G2 to G5 in under an hour, and the main body of the CME was still arriving. Low Earth orbit became a shooting gallery. The sudden compression and subsequent expansion of Earth's magnetosphere drove a surge of high-energy particles into the radiation belts. Satellite operators received a flood of automated alerts as systems switched to safe mode, one after another. 3 commercial communications satellites reported total loss of attitude control. Without stabilization, they tumbled helplessly, solar panels spinning away from the sun, batteries draining. Mission controllers worked frantically to regain command before power ran out completely. GPS accuracy degraded across the board. Navigation systems worldwide showed position errors of 50 meters or more, enough to ground aircraft relying on precision approaches, and to send shipping lanes into manual navigation mode. The Starlink constellation, with thousands of satellites in low orbit, experienced dozens of unexpected atmospheric drag events as the storm heated and expanded Earth's upper atmosphere. Several satellites dropped into decay orbits, their demise now inevitable. At 22:15 Universal Time Coordinated, a critical satellite failed. SES-17, a high-capacity broadband satellite serving internet and communication across the Americas, went silent. Engineers suspected a microprocessor upset caused by high-energy protons punching through shielding and flipping bits in the flight computer's memory. Recovery attempts began immediately, but the satellite remained unresponsive. Millions of users lost connectivity. As the G5 storm raged, amateur astronomers and professional observers turned their instruments skyward, capturing not just the aurora, but something unexpected. The debris field from 3I/Atlas, now spread across millions of kilometers, was producing its own light show. Meteor cameras in the northern hemisphere recorded dozens of bright fireballs, not the usual sporadic meteors, but fast-moving objects on nearly parallel trajectories. Spectroscopic analysis of the meteor trail showed the same unusual chemical signatures JUICE had detected: high CO and N2, with almost no sodium or iron. These weren't ordinary meteors. They were fragments from a shattered comet, microscopic pieces racing through the solar system at over 30 kilometers per second. Earth was in the direct path of the debris field. Atlas's hyperbolic trajectory ensured that, but the outer edges of the comet's expanding cloud were grazing Earth's orbit, close enough for our planet's gravity to capture the smallest particles. For 3 hours, observers recorded a slow drizzle of interstellar dust, the first time in history that material from beyond our solar system had been directly detected entering Earth's atmosphere. The scientific implications were staggering, but they were buried under the more immediate crisis unfolding on the ground. Just as engineers thought they had stabilized the grids, the merged second and third CMEs arrived. This impact was more glancing, but it rekindled the geomagnetic storm just as it had started to subside. The aurora brightened again, pushing south past the 35th parallel. In some regions, the lights were so intense they cast shadows. Transformer temperatures, which had begun to fall, spiked again. At a major substation outside Chicago, a 345 kV transformer, already stressed from the first wave, reached its thermal limit. The oil inside, designed to insulate and cool, broke down under the electromagnetic onslaught. At 1:47 Universal Time Coordinated, the transformer failed catastrophically, its core fusing into a useless mass of melted copper and steel. The cascade began. Power rerouted through neighboring transformers, which immediately overloaded. Grid operators faced an impossible choice: shut down large sections of the network or risk losing even more transformers, equipment that takes months to replace. They chose shutdown. By 2 o'clock Universal Time Coordinated, over 40 million people across the Midwest and Northeast had lost power. In the darkness, only the aurora shone. By sunrise, the worst had passed. The geomagnetic storm finally dropped below G4 as the bulk of the plasma stream swept past Earth. Power began returning to most regions, though full restoration would take days. The final tally was sobering, but could have been far worse. 14 major transformers destroyed, with a combined replacement cost exceeding $400 million. 7 satellites lost or permanently damaged. GPS degraded for 18 hours, causing disruptions in aviation, shipping, and precision agriculture. Total economic impact estimated at $6 to $8 billion. 0 casualties, thanks to early warnings and aggressive protective measures. The operational response had worked. Forecasters, grid operators, and satellite controllers had bought just enough time to prevent a catastrophe on the scale of 1859 or 2003. But it was close, far too close. 3I/Atlas continued outbound, its fragments spreading into an elongated stream that would eventually disperse across the inner solar system. JUICE's observation provided the first detailed look at an interstellar comet's death, and the data would fuel research for decades. The meteor observations offered a tantalizing glimpse of material forged in another star system, now vaporizing in Earth's atmosphere. But the real story wasn't about the comet. The solar storm of November 4th to 5th, 2025, became known as the Atlas event. Not because the comet caused it, but because the two phenomena intersected in a moment that forced the world to pay attention. 3I/Atlas had been a messenger, its violent death a preview of forces that humans could observe but not control. In the weeks that followed, funding for space weather forecasting tripled. Grid hardening projects, languishing for years, received emergency appropriations. Satellite manufacturers accelerated radiation hardening programs. The public, which had watched the aurora in wonder, now understood that the same processes painting the sky could also bring modern civilization to its knees. The interstellar visitor had come and gone, shattered by our sun's fury. But it left behind a stark reminder: we live at the mercy of a star that can be beautiful, life-giving, and terrifyingly powerful, sometimes all within the same day. And above us, always, the sun continues its dance. The next storm is already brewing in the roiling magnetic chaos of its surface, waiting for the right moment to unleash itself toward Earth. We watch. We prepare. We remember the night when an alien comet and our own star taught us how fragile our grip on technology really is, and how spectacular the universe can be when it reminds us of our place within it.